Good morning, students. So in the last class, we have winded up the second module with threads, user level threads and kernel level threads. And in today's class, we will start with the third module, that is memory management. Right. So we have already seen in the first module that operating system will assign some memories. Memory can also be considered as a resource, one kind of a resource, right? So this memory is also assigned to user process by the operating system, right? And it can assign different kinds of memories, right? So the memories are classified into three different types. One is called actually two. One is main memory, second one is the secondary memory, right? Or main memory is also called as a primary memory, right? So in ROM and RAM, they fall in main memories, and hard disk, then floppy, then CD drives, tape, these all magnetic disks, right? So these all fall under secondary sorry secondary memories, right? So the primary memories are very fast and they are very small in size, and secondary memories are very slow and they are big in size, right? So whenever you are assigning, whenever you are running a process or a program, right? So let us say programs are stored in a disk or a secondary memories, right? So those programs which are stored in a secondary memories, they have to be brought into the primary memories before they start execute and they start their execution, right? So without loading from secondary memory to primary memory, we cannot execute a program, or we cannot do anything with any of our tasks which were associated with the computer system, right? So in all computer systems, the programs or the tasks which has to be brought to the main memory for their execution, right? So hence only we say uh, when we are choosing electronic device, we always choose the electronic device with the highest RAM, with the more size of RAM, because the number of instructions or the number of programs which has to be handled by the RAM should be very high, right? So if we take a lesser size of a RAM, then the speed of execution of those programs will also be less, because um, it can accommodate only little number of programs, right? And even the speed of execution will be very less, right? So we go for always high size of or more size of RAM, right? Because it can accommodate a very large number of programs or processes, or you can say different tasks, and it can run with a higher speed, right? So for these two reasons, we are going to use a very high size of RAM, right? And even RAM, which is also called as a non-volatile memory, sorry, volatile memory, because once the power goes off, whatever we loaded in the RAM is vanished, or it gets destroyed, right? And we have one more kind of memory which we call it as ROM, and it is also called as non-volatile memory. And why it is called non-volatile memory? Because the data is not going to be erased even when the power goes off, right? So for that reason, it is called a non-volatile memory, and all the operating systems and booting programs, all those are loaded in ROM, because even the computer system is turned off, the ROM content should not be erased, or the contents of memory should not be erased. If we store those programs, operating system programs or booting programs and all in RAM, once the power goes off or once the computer system is shut down, then we are going to lose that data. So we have to again load the operating system into those memories, right? So for this reason, the operating systems are not going to be stored in volatile memories, they are going to be stored in non-volatile memories, right? So now we will see what are the different hierarchies of these memories, right? So we can also have a small memories on the processor itself, or inbuilt memory, what we can call. we can call them as, we can also call them as general purpose registers, right? So but these registers are very fast, right, but they are very less in size. They hardly available in 1 byte or 2 bytes, maximum we can say 4 bytes, not more than that, right? And along with this we have one more kind of memory which we call it as cache, which we call it as a cache, right? So what is the use of cache? More frequently used programs or more frequently used instructions are going to be stored in cache, right? So whenever the CPU wants to fetch, wants to execute those instructions, they'll not again see it into the main memory, right? So the computer central processor unit always fetches the cache memories first. Before that it will fetch the registers. They cannot store the large size of instructions. They can only hold the present content of those registers, right? So we have one more very fast memory called cache, is is also implemented along with these primary memories and secondary memories, right? So always central processor unit is going to fetch the instructions or the data from first from the cache, right? First it will look into this memory, that is cache memory. If it doesn't find any data or instructions what it needed, then only it will go to the main memory. If it doesn't find in main memory, then it will go to the secondary memory, right? So first it will fetch the data from cache. If it is not available, then it will jump to the main memory, right? So here memory, it is a main memory. This is a main memory, either RAM or ROM. But ROM we doesn't include a ROM for storing the data. It is used only to store the operating system programs, or what we call a boot procedure programs, right? And if it doesn't find any data in the main memory, then it will look into the secondary memory, right? So but this is not the operation of operating system, right? So first it will look into the cache, right? So here we have one more part of the program, one more part of the operating system, which we call it as MMU in short, that is called memory management unit. So this memory management unit is going to handle all the operations regarding the memories, right? So if it doesn't find in cache, then it will look the data, what processor is looking for the data, so that data will be looked by MMU into the main memory. If it doesn't find in the main memory, then it will switch to disk memory or secondary memory, right? So if it finds the data in secondary memory, then it will be loaded into primary memory, and later it will be loaded into cache, right? And CPU directly fetches the cache, right? So we have level 1 and level 3 caches, right? So why they are called, why they are classified into different levels? Because cache is available only in very little amount of very little size. It has only it is in the form of KBs, right? So even you can include more number of caches to include to increase their sizes, but we do not go for very very high number of caches, because it will make your computer system very big, right? So we will include hardly 2 or 3 levels of caches are included. After that we will go with the primary memory, that is either that is RAM, right? So this is the memory, basics of memories, right? Volatile memory, non-volatile memory, primary memory, secondary memories, caches, right? So these are all the different kinds of memories in which the computer systems are going to fetch, right? So now so why it is called a virtual memory? Why memories and disks are called as a virtual memory? Because always CPU will look into the cache first, right? So if data is not available, then it is going to fetch the data from memory, and that will be handled by the memory management unit, right? So CPU is not aware of these two memories, right? So for CPU, these two memories can be called as a virtual memory, because these are physically available in the computer system, but CPU doesn't think that they are available in the physical computer system. It will just think that only cache is available for me, right? Always, whenever the data is looked by the computer system or a central processor unit, it will be always fetched from the cache, right? So if it doesn't find in cache, then the memory management will help the uh, data to be loaded from memory to cache. Okay, so CPU is not aware of these two memories, primary memories and secondary memories, hence they are put in one category called virtual memory. Virtual memory in the sense it is just an imaginary memory, right? So for user is aware of these all, right? So user when you are looking in from a user point of view, then I cannot call these two memories as virtual memory. These are also called as physical memories, which are available on the computer system. But when you are looking from the CPU point of view, the CPU will always think that only cache is available for me and other two are not physically available in the computer system, right? So from CPU point of view, only cache is available physically and other memories are available virtually, right? So here in the table there are different levels of memories, right? So one is cache, I just discussed, memory nothing but a main memory, and disks nothing but a secondary memory. How they are going to be managed? Allocation and use is managed by the hardware, that is nothing but a memory management unit. Allocation is managed by the kernel and use of allocated memory is managed by runtime libraries, right? So kernel is going to manage all these memories, right? Allocation and use is managed by the kernel, right? So here this allocation of cache to the user process is managed by the hardware, which is nothing but the memory management unit, and primary memory and secondary memory allocation is always handled by the kernel, that is heart of the operating system. So what are the performance issues? Cache ensuring high hit ratios, because CPU will also always look at the cache, look the data into the cache first. If it is not available, then MN will come into picture, and MN will help to load the data from main memory to cache, or from secondary memory to main memory, then main memory to cache. Second one, primary memory. What is the performance issues here? Accommodating more processes in a memory, because it has more size compared to cache, right? So it accommodates more process in a memory, and the frequently used data and the code is always available in cache. Second one, ensuring high hit ratios, because if the data is not found in the cache, then the next level of memory is nothing but the main memory, that is RAM. If it is not available, then only it will go to the secondary memory. Otherwise, always it will find the data in main memory, right? So it also ensures that the high hit ratios. High hit ratios in the sense, whenever the CPU looks for any kind of data or the code, that has to be available in the main memory. That is nothing but a high hit ratios. Instead of going to the secondary memory and loading the data or code from the secondary memory, always the data will be available at the main memory. Even if it is not available, the computer system or the memory management unit should not take much time to load that data or code from the secondary memory to primary memory. And the last one, that is secondary memory disk. What are the performance issues? Quick loading and storing of parts of the process address spaces. That means address space you just leave. Later you will understand. Just think about the process, right? So process or program which are loaded in secondary memory, that has to be loaded into the main memory very quickly by the memory management unit, so that the computer system should not take more time to execute any process or a program, right? So this is all about the basics of memory and the hierarchies of memory, right? So in next slide we will see what are the memory allocation modules, right? So what are how if I allocate a particular memory, how that memory is utilized by the process, that we are going to see now. That is memory allocation model. The kernel creates a new process, right? When a user issues a command to execute a program, right? So whenever a user writes a program, and when it is connected to a linker and a loader, that process will program is converted into process, right? And kernel creates a new process to execute that code, to execute that program. So at this time, it has to decide how much memory it should allocate to the following components. So what are the different following components in a process? We have different following components like code and the static data of a program. That is the actual program of a actual program, which is nothing but a code, and static data. Static data is in the sense, as the program runs, these data are not going to change, right? So it should allocate a memory for a code, it should allocate a memory for data, that is static data, which is not going to change throughout the program. And third one, it is going to allocate some memory for a stack, that is whenever the program includes the number of functions, right? So whenever the functions are called in a program, then stack will come into picture. So stack is going to hold the local what you can call the local parameters as well as the return address of that particular instruction. So that is going to be stored on a stack, right? So even kernel should allocate a memory for stack. And the last one, program controlled dynamic data. As the program goes on running, goes on execution as it continues, then some of the data is going to change dynamically, right? So as the execution of a program proceeds, then the content of some variables are going to change, right? So that kind of data is called program controlled dynamic data. That means the program is going to control the data available in those particular variables, and which is also called as PCD data, program controlled dynamic data, right? So after allocation of a memory, right? So how that memory looks, let us say this is a kind of memory. I'll say it as a 1 MB of memory, right? So enter this 1 MB of memory is allocated to a kernel, allocated to a process by the kernel, right? So how this 1 MB of memory is divided? It is left to the kernel. It will allocate some part of this 1 MB to code, then part of that 1 MB to static data, then PCD data, program controlled dynamic data, and the last one, the stack data, right? So some portion is going to remain free, because I don't know what size of memory is going to be used by the process, right? So always kernel will allocate some memory in excess, right? So here low end of the allocated memory, and this is high end of the allocated memory, right? So if the memory size or a memory address will always start from 0 and it ends at 1 MB minus 1, because it is starting from 1. It is starting from 0. So what is the last address of a memory? Then it is 1 MB minus 1. If it is 2 MB, then it is 2 MB minus 1, because the address is going to start from 0, and this size of the address is also called as address space, right? So it always starts assigning the memory from 0, right? So from 0 it starts assigning the data, the memory to first code, then it will assign a memory to static data, then it will assign memory to PCD data, then stack will always start from the last memory address. Stack grows in opposite direction compared to the PCD data, right? So in between PCD and data and stack data, you will find some free space, because always there will be excess memory which is allocated by the kernel to a process. So this is about the memory hierarchy and the memory allocation model. In next slide we will continue this model. Okay.